Let's take a moment and go through the underlying concept and then also how to do some of the calculations for the second day of the KSP lab. In this part of the lab, we are working with a saturated solution of lead chloride, and the goal being to find the KSP value for the saturated solution. Given that the solution we use is a saturated solution of lead chloride, an equilibrium exists in the solution between the PbCl2 solid and its aqueous ions, lead ions and chloride ions. The KSP expression for this equilibrium would be the Pb concentrations, the lead ion concentration, times the chloride ion concentration squared. The goal in the lab is to find a numeric value for the KSP for this particular equilibrium. To do that, we have to experimentally determine the concentration of the lead ions and the chloride ions when the system is at equilibrium. We can then insert the lead ion concentration and the chloride concentration at equilibrium into the KSP expression and calculate a value for the KSP. In the saturated solution of PbCl2, the amount of ions that are present, the amount of ions present in the solution are ions that would be at equilibrium concentrations. The reason these would be at equilibrium concentrations is because when the system is saturated with the solid present on the bottom and aqueous ions present in the water, this would be an equilibrium situation. So the lead concentration and the chloride concentration in the saturated solution would be at equilibrium concentrations. Procedurally, what we did in the lab is to take some of the lead chloride solution and measure out 100 milliliters of saturated lead chloride solution and pour it into a beaker, being careful to leave the solid sediment behind so that all we have in the beaker are equilibrium amounts of lead ions and chloride ions. If we can now experimentally figure out the concentration of our lead and chloride ions, that would allow us to have the equilibrium concentrations of lead and chloride and allow us to calculate the KSP value. What we're going to use as a tool to find out the concentration of the lead ions is a single replacement reaction using elemental zinc. In this reaction, the elemental zinc reacts with the ions of lead and turns into zinc ions and lead solid. We measured the mass of a piece of zinc and then dropped the zinc into the lead chloride solution. What's now going to take place is as the lead ions touch the elemental zinc, the single replacement reaction takes place. And this reacts in a 1-to-1 ratio. The limiting reactant in the reaction is going to be the amount of lead ions that are in the solution. The lead ions will run out, completely exhausting all of the lead ions in the solution, and the reaction will stop. When the reaction stops, we remove the zinc strip from the solution, reweigh the zinc strip, and the mass of the zinc strip will have gone down because some of the elemental zinc will have turned into ionic zinc. Meanwhile, all of the lead ions will have turned into solid lead, elemental lead. The change in mass of our zinc strip allows us to figure out how many moles of zinc reacted. Because the zinc and lead react in a 1-to-1 ratio, if we know how many moles of zinc have reacted, that tells us how many moles of lead ions were present in the solution. And if we know how many lead ions were present in the solution, we also then can know how many chloride ions are present in the solution, because 2 chloride ions form for every 1 lead ion. Let's do a sample calculation with some example data for how to calculate the KSP value. From our data, the before mass is 4.38 grams. After the completion of the reaction, it's 4.28 grams. The mass of zinc that reacted overnight would be 0.10 grams of zinc. We want to now switch this to moles of zinc. From the periodic table, we know that 1 mole of zinc is 65.38 grams. We can now use a proportion. Knowing 1 mole of zinc is 65.38 grams, that means we'll have X moles of zinc present if we have 0.10 grams. This will let us calculate the moles of zinc that reacted. Solving for X gives us 0.0015 moles of zinc. The single replacement reaction that took place in the beaker overnight between the zinc solid and the lead ions reacts in a 1-to-1 ratio. Since we now know that 0.0015 moles of zinc reacted overnight, that tells us then that 0.0015 moles of Pb2 plus ions must have been present in the beaker when we put the lead into the beaker. Since we now know that the sample we used had 0.0015 moles of lead ion, and looking at the balanced equation for the saturated solution, we can see that for every 1 lead ion that gets put in the solution by the lead chloride dissolving, there's 2 chloride ions. Therefore, the solution has, in addition to the 0.0015 moles of lead ions, there's 0.0030 moles of chloride ions present in the saturated solution. Now the KSP expression for the saturated lead chloride solution, to make this work, we need to put in concentrations at equilibrium inside the bracket. Since we now know the moles present, we have to convert the moles into concentration. The sample size that was used in the lab was a 100 milliliter sample of the saturated solution. So we can now find the concentration of each of these ions since we know the moles and the liters that were present. What we know is that we have 0.0015 moles of lead ions present in a 0.100 liter sample, which means we'd have X moles of lead ions present in a 1 liter sample. Once we have this in terms of how many moles are present in 1 liter, that's our concentration. Solving for the concentration gives us an equilibrium concentration in the saturated solution of 0.015 molar lead ions. What we can do with this concentration for the lead ions is place that into the equilibrium constant expression for the equilibrium concentration of lead. Now, because the number of moles of chloride ions present is double the number of lead ions from the 1-to-2 ratio in the balanced equation, the concentration of the chloride ions will be double the concentration of the lead ions. So we know the chloride concentration is going to be 0.030 molar, and then we still have our square here from the 2 in the balanced equation. This will now allow us to calculate an experimental value for our KSP value. The experimental value we get for our KSP is 1.35 times 10 to the negative fifth. This would now let us calculate an experimental error for our lab, where experimental error is the absolute value of the known minus the experimental divided by the known. We can use the known KSP provided, that's 1.7 times 10 to the negative fifth. The last part of the lab is something that's about something known as the common ion effect. The common ion effect is where we add an ion to the equilibrium that is common with one of the ions already present in the equilibrium. For example, here we have our saturated lead chloride solution. If we were to come along to this now and add, say, a solution of sodium chloride that is aqueous, that's going to cause the amount of chloride ions in the solution to increase. Now, as we look at the equilibrium, if the chloride concentration increases, the equilibrium will respond to that change by shifting to the left, and visually, by shifting to the left, we would see more solid forming in the solution. Now, the effect of this is, because we see more solid forming, by adding chloride ions from an outside source, in this case sodium chloride, that shares the same chloride ion that's present in the saturated lead chloride solution, the chloride concentration again goes up. This drives the reaction to the left, making additional solid form. The additional solid forming is a visual indication that the lead chloride has actually become less soluble from the addition of the sodium chloride solution. If something is more soluble, more of the solid would dissolve. If something gets less soluble, more solid remains solid, indicating that less of the material has the ability to dissolve. So increasing the chloride ion concentration drives the reaction left, more solid forms, and this actually causes the solid to be less soluble in this solution. Let's look at another system with the common ion effect. Here we have a system that's saturated, and it's going to be at equilibrium. Iron sulfide. Now it says if we add addition extra S2 minus ions, it could be from something such as, say, sodium sulfide. Sodium sulfide shares sulfide ions with the sulfide ions that are in the iron sulfide. This will cause the sulfide concentration to increase. Increasing the sulfide ion concentration drives the reaction to the left, trying to get rid of the excess sulfide. Now visually, what we would expect to see as we add extra sulfide ions to the solution, when the reaction shifts left, it's going to produce additional solid. So we'd see extra solid forming in the bottom of our container, indicating that the iron sulfide from the addition of the sulfide ions has actually now become less soluble, producing more of the solid precipitate as a result of the reaction shifting to the left to get rid of the excess sulfide ion. So in response to this question, after the shift, since we saw more solid form from the reaction getting driven to the left, that means the solubility of the iron sulfide is actually now less soluble because more solid has been created. Another way to look at this, mathematically, if the S2 minus concentration goes up, for this to remain equal to the equilibrium constant, that means the iron concentration has to go down. The iron concentration is going down because it's being taken up in the formation of additional iron sulfide solid. A lesser amount of the iron ions present, because we've added sulfide ions from an outside source, means that the iron ions becomes less, which means the iron sulfide is now less soluble because less of the material is dissolving into aqueous ions and more of the solid is remaining present. Taking this now another step, if we were to take some iron sulfide solid and add some iron sulfide solid to different solutions, depending on the amount of sulfide ions or iron ions present in the solution, can affect the solubility of the iron sulfide. The KSP expression for iron sulfide is Fe2 plus concentration times S2 minus. Our first solution is something that's 0.5 molar sodium sulfide. So this already has present 0.50 molar sulfide ions in the solution. If we were to try to add some iron sulfide to this, because there's sulfide ions present, they will inhibit the ability of the iron sulfide to dissolve. The sulfide concentration, if this is high, then the iron concentration is going to be low. If the iron concentration is low, that indicates that very little of the iron sulfide is dissolved, meaning that it is less soluble. The greater the amount of sulfide ions present in the solution that we're adding the iron sulfide to, the less soluble the iron sulfide can be because there's already sulfide ions present. Consequently, the iron sulfide will end up being most soluble in the pure water because the pure water lacks any additional sulfide ions. It'll be least soluble in the 2 molar iron sulfide because the concentration of the sulfide ions is already 2 molar before adding any iron sulfide to the solution. The order of solubility would reflect how much sulfide is present in the solution before adding the iron sulfide. Most soluble is pure water. Next would be the 0.10 molar sulfide concentration. Third is 0.5, and least soluble would be when there's 2 molar sulfide ions already present in the water before we add the solid iron